Alright guys, welcome back. In this video we are starting to talk about strain energy and strain energy density. So if you imagine that we have a member here of length L with cross-sectional area of A, and we apply a slowly increasing load to it of P, then we're going to be getting a corresponding deformation. Now we can plot that here with our applied load on this axis and our deformation down here. But basically, as the member deforms, the load is doing some work. And work is just force times distance. So let's use some calculus and we'll find the elementary work done by P as it moves a tiny distance of dx. So basically we're looking for this little sliver of area in here. Strain energy is represented as a capital U. So for the elemental work we just have du is going to be equal to p dx. And if we want to find the total work done to get to this deformation of x1, then we just find the area that's just from x equals 0 to x equals x1. And basically just integrate the area, or find the area under this part of the curve, so we'll be left with just with the integration from 0 to x1 of p dx. Now in the elastic range or straight line section of this graph, the expression for P is just going to be equal to kx. And what we can do with that is when we're looking for strain energy, we'll plug this in, we'll basically substitute P for kx here. So we had 0 to x1, and where we have P we will write kx, and then we had dx. Alright, so kx is a constant, so we're going to bring that out. So from 0 to x1 we have x dx, and this simplifies just to 1/2 k x squared. Now we should put in the subscript here of x1 because we substituted in here x1 and 0, but the zeros obviously just disappeared, so now we have x1. Now talking about this though, kx is equal to p, and this is really saying is we have 1/2 k x1 x1, right? That's just squared. So if kx is equal to p, then we can rewrite this as 1/2 p1 x1. So this is our expression for strain energy, where we have strain energy is equal to U is equal to 1/2 p1 x1. And basically the strain energy of a member is just the increase in the energy due to the deformation of that member. And the other thing to mention is that strain energy is in units of joules, which is newtons times meters. And when we look at that, that's what we do have. We would have newtons here times meters. So for strain energy, this is all based on a member with length L and a given cross-sectional area. But in order to be able to talk about members with any dimensions and like basically compare apples to apples, we need to divide by the volume to get strain energy density, which is going to give us the energy per unit volume. For example, this will be in units of like joules per meter cubed instead of just joules. Alright, so let's give ourselves some space, and what we want to do is basically work with this expression here, and we want to divide out the volume to be able to get the strain energy density. So let's just put this over volume. And we'll put this over volume, or in this case, because this is some kind of rod, we can say this is the cross-sectional area times the length. Now, when we look at this, we have some important things here. We have P over A in this side of the expression, and that's just equal to our normal stress. We also have, if we look at X over L, that's the normal strain. So if we have X over L, that's equal to normal strain. And if we have dx over L as we do in this expression, that gives us basically our little elemental strain just like that. So we can substitute some of these things in. And when we talk about capital U over V, this is strain energy density. So this actually drops down. We can say that, maybe I'll write it over here, capital U over volume is equal to lowercase u, and this is equal to strain energy density. So we can go and substitute some of these things in here now. So we'll write this as lowercase u, and we'll have our integral here. When we'll substitute p and a for our p over a for our normal stress, and then we'll substitute this here for our d elemental strain there. And then this means that we'll have to go from 0 to strain to E1 there, or epsilon 1. But we also have Hooke's law, where we have the normal stress is equal to E times epsilon. So we can plug that in here as well and rewrite this. So we're going to get strain energy density is equal to 0 to epsilon 1 of E times epsilon x, and then we have d epsilon x. Okay, so we'll pull out the capital E here, as it is a constant, so we have E is equal to 0 from 0 to epsilon 1 of Ex d Ex, and this basically just simplifies to 1/2 E epsilon x squared. Now, with Hooke's law again, we have we can just rearrange this. So we have epsilon x is just going to be equal to normal stress over E, just like that. So basically, what we can do is we can substitute that in here. So we're going to be getting 1/2 E, and then we'll just substitute all this stuff in. So that was squared. So we have squared over that squared, right? It's coming from us right there. And we can simplify this. We have 1e in the top, 2 in the bottom, and then let's just rewrite this a little bit cleaner. So we'll have sigma x squared over 2e. So that is our strain energy density. That is on a per unit volume. So we have, again, we'll just write it here a little cleaner. So we have sigma x squared over 2e. And if we go right up to the end of the elastic section, then we're just going to find what's called the modulus of resistance, which is basically the strain energy density once we are all the way to the yield point. So that's just going to be sigma y for the yield point, or the yield stress, and that's over 2e. So basically, if we just draw the stress strain diagram for this for whatever material we're looking at, it's going to look let's see, it's going to look something like this, right? It'll have the linear elastic section, and maybe if it's steel or something, it'll look something like that. But if we basically plot this area in here, or calculate the area in this section, this is what we call, so we've gone all the way up to the yield point. This is basically what we call the modulus of resistance. And this tells us the energy per unit volume that a material can absorb before it yields. And then if we went right to the end here and took this area all the way from 0, then this is what we call the modulus of toughness, which tells us the energy per unit volume that a material can absorb before it ruptures. So those are two very important things based in these equations, and I think that's where we're going to cut it off for this video. Join me in the next video, and we will go through some examples on this stuff for axial loads and bending and torsion and all those things. Alright, see you guys there.